All right, we're excited to welcome Aaron Romero to the stage from Palo Alto Networks. Aaron is from San Francisco. After graduating from San Jose State University with a BS in EE, he worked as a server platform engineer for 4 years. After joining Palo Alto Networks in 2019, he transitioned to DevOps as database admin. In his free time, Aaron enjoys golf and rock climbing. Please give a warm round of applause to Aaron. Thank you, Aaron.
Thanks. Okay, so over the past year, we have spent a lot of time working with MongoDB, and they've helped us, really, find all the pain points that we've been experiencing with our MongoDB clusters. And with their help, we've been able to implement a lot of monitoring to help us, identify the problems that we're having, implement fixes, and make sure that these problems don't come back. So by the end of this presentation, I hope you can take away some of the common practices that we use daily to help keep our cluster healthy. So first, let me tell you a little bit about us. Zingbox IoT was founded in October of 2014. And what Zingbox offers is a cloud-based solution to securing all of your IoT devices. And in September of 2019, Palo Alto Networks acquired Zingbox to lead their IoT security solution. So if you look at the diagram here, this represents our IoT security lifecycle. And this is what we follow to continuously discover your devices and keep them secured. And this cycle begins at number 1 here, understanding your IoT assets. The first thing we do is discover your devices. We figure out what types of devices they are, what software they're running, and who they're talking to. Second, we assess the IoT risks. We calculate a risk score for all of your devices based on vulnerabilities that it might have. The more severe the vulnerabilities, the higher the risk. And third, we apply risk reduction policies. Right? We make suggestions to better secure your devices based on the vulnerabilities that we detect. And once you do that, that leads us to number 4, where your devices are now prevented from known threats. And number 5, we detect and respond to unknown threats. Our machine learning has built an extensive knowledge base of how your devices are supposed to behave. And since we know how they're supposed to operate, it's very easy for us to detect anomalies. Right? And this leads us back to number 1, where we rediscover your devices, and the cycle continues to keep securing your network. So here's the agenda for the rest of this presentation. First, we'll cover our data critical path architecture. Second, why we chose Atlas. 3, how we measure cluster health. 4, identifying our bottlenecks. And 5, implementing cluster visibility. So first, let's go over our data critical path. Now, this is our end-to-end pipeline. It's a real-time pipeline. So data gets ingested and it gets processed real-time and is made available as soon as possible for our customers to view. So the first component in this end-to-end pipeline is Cortex Data Lake. All of our customers' firewalls that are subscribed to our Zingbox services, their data gets uploaded to Cortex Data Lake. And their raw device data then gets forwarded over to Kafka, which we use as our data streaming service. This data then gets consumed by our backend services, where they'll perform data aggregations and machine learning to learn about your devices. Then the data gets written to MongoDB, which serves as 2 purposes for us. 1, as a reporting database, where our users can query their data, and second, as a data warehouse, where data is going to be stored for further machine learning. And finally, our end users are able to view their data in their customer dashboard. Now, this data critical path directly affects the customer. Right? Any delay in this pipeline means delayed data for the end user. And the problem with this is if we have delayed data, we run the risk of putting our customers at risk. We won't be able to alert them the second that a threat occurs, right? So any component in this pipeline, can cause delay. But for the purposes of this presentation, and for me personally, I want to make sure that MongoDB is not the bottleneck, right? I want MongoDB to run smoothly and not cause any delays. So let's take a look at why we moved to Atlas in the first place, right? Because as a startup, we didn't always have Atlas, right? We managed our clusters ourselves in our own personal AWS clusters. And it came with a lot of headaches, as you can see from the left side, the list on the left side, right? So the first thing here is we had over-provisioned and underutilized clusters, right? So As a fast-moving startup, when we run into performance issues, the easiest thing for us to do was just to scale up, right? So, at times we would even have like 20% utilization just because we have so many resources, which leads me to number 2. We have high cost because of that. And 3, because we're managing these ourselves, we have outdated hardware and software. It's hard to stay on top of it and always have the most current hardware and software. And number 4, when we do these updates, it's very labor intensive. It takes a lot of effort and time away from me and my team to do these maintenances. And number 5, because it's so labor intensive, none of this is really scalable, right? It takes a lot of time and effort for us. And as we continue to grow, as we continue to get more customers and data, it's going to take a lot more of our time. So now let's take a look at the benefits that Atlas gives us. They're able to actually address all of these concerns that we once had. So first, we were able to consolidate all of our clusters to Atlas, right? So we would have clusters that have 20 plus shards, and they were able to be put in a single Atlas cluster of about 4 to 6 shards, depending on the data. And because we were using less resources, we were actually able to reduce our overall costs. And third, this kind of goes without saying, but Atlas is a managed service, so we don't have to manage the hardware or software anymore, right? And number 4, when they do manage the hardware and software, the maintenances are pretty seamless. We don't really recognize that it's going on. We don't see performance degradation. And if you have any doubt about it, you can schedule them during non-peak hours. And number 5, Atlas is very scalable. Whereas before, when we needed to scale a cluster up or down, even with automation, this took time, right? We had to build up the instances, we need to configure them, attach them to the cluster, wait for the data to balance out. But now, if we need to scale up, scale out, it can all be done with the click of a button. So all in all, it was a pretty effortless decision for us. We get to get some of our time back. We don't have to manage it anymore. And we can do this all at a reduced cost. So now let's talk about how we measure cluster health, right? What metrics matter the most to us? And when those metrics indicate poor health, how do we identify the issues? So our main KPI, or key performance indicator to measure our cluster health, is write tickets. And you can think of write tickets as the amount of threads that Mongo has to process incoming requests. And if you take a look at the top image here, this depicts the amount of available write ticks of an unhealthy cluster. Right? If you look at all of the graphs here, all these graph lines represent a different shard in our cluster. And this green one in particular is very unhealthy. You can see that it dips down to the bottom of the graph, meaning it has 0 write tickets. Right? It has no more resources. They're all exhausted. It can't take on incoming commands. And this leads to high queued writes, right? Those incoming requests, they have nowhere to go, so they're going to get queued up, waiting for resources to free up. And this creates lag in our pipeline, which, again, I said, it puts us and our customers at risk. So now this is just the symptom that we see of an unhealthy cluster. But what's really causing this, right? We have to figure out what's causing it, what's the underlying issue. So like I said before, we've been working all year with the Mongo team to help identify what the actual causes are that are causing these low write tickets. So here are the major ones. We have long-running queries, inefficient queries, improper indexing, hot chunks, large documents, and imbalanced shards. And together, these all contribute to giving us low write tickets. So let's go a little deeper into each of these. First, let's talk about identifying slow commands. And Cloud Manager actually gives us a lot of tools to do this. First being Profiler. And Profiler actually does exactly what we want it to do. It gives you the worst case scenario. It gives you the slowest commands, the longest running commands in the last 24 hours. The next tool is the real-time analyzer. And as the name indicates, it tells you what's going on in your cluster right now, right? How many operations are running, what are the hottest collections, what are the slowest commands that are running right now. The Performance Advisor. This is a very helpful tool for us because it analyzes your most inefficient operations and gives you immediate feedback and suggestions on which indexes to add to directly, immediately improve your performance. So this is something that's very easy to use, it's actionable, and you should be able to see performance differences immediately. And lastly, of course, we have a whole history of cluster metrics, right? Me and my team use this daily to see the overall health of the Mongo cluster and how our applications are affecting it day to day. And it's easy to make correlations when an event happens. Now, in addition to all of these great cloud manager metrics, we also have our own homegrown monitoring. Right? So we've set up this scanning job that scans the MongoDB op log and monitors all the incoming operations. And we can group all of these operations by things such as collection, schema, and type. And with this information, this visibility helps us identify a few things. So one is most frequently used commands. So this is very important to us because take, for example, let's say we have an operation that takes 100 milliseconds to run. By itself, it's pretty harmless, right? But if this is running thousands of times a second, it could potentially be an issue with your database. And of those, we can see which have the highest execution times. Like we already had this from Profiler, but now we have an overall view of what's running in our database. We have every single command that's coming in, and we can check what the execution time is. And lastly, of these commands, since we know the schema, we know which ones are supported by indexes and which ones aren't. So here's one example of one of our graphs depicting our data. This shows the frequency per hour of every single command running in our database. And I hope you can see that there are two that stand out from all the rest. We have two commands that during their peak hours, that they can run up to a few 100,000 times an hour, which is far greater than the other ones. Like the data is so skewed, every other command kind of looks like they're at zero. And so now that we've been able to identify which commands are our heaviest right now, we can now correlate this to our other graph, which shows execution time. Right? We can see if these heaviest, the most frequent commands are running, taking seconds long. That we're probably in trouble if that happens. And we can make improvements. Do we need to change, a change in index, right? Do we make improvements with the indexing? Do we need to go back to the drawing board and do a whole redesign? Because data changes over time, and what we used to work in the past may not work anymore. And the good thing about having metrics like this is that you can see how it tells a story over time. As your data changes, maybe the performance gets worse over time and you'll need to make changes. So the next issue I want to talk about is hot chunks. And a hot chunk is defined as a chunk that's heavily written to. So ideally, what you would want is to have an even distribution of load all across your chunks. But for us, this is not really the case. So let me give you an example. Our heaviest collection and most heavily written to collection is our session collection, right? And this session collection, it holds all of our session data. And let me define what a session is, first of all. So think about if I have a device, right? It's going to be talking to other devices, sending data. Each of those endpoints is essentially a session, right? So the more devices it's talking to, it could be talking to devices over here, devices in the cloud. Those are session data. So if you take a look at the image on the right side here, this is an example of a chunk in our session collection. And our sharding key of choice here is a compound one. Right? The primary key is device ID, which is the MAC address of the source device. And the secondary key is the remote IP, which is of the destination device. Okay, so hopefully now you have a better understanding of how data is going to be organized in this session collection, right? Primarily by the source device ID. So back to hot chunks. One of the possible causes for hot chunks is what we call a jumbo device. And a jumbo device is something that has a lot of endpoints, right? So for example, a scanner. A scanner device could be something that you deploy to monitor and manage multiple devices, right? It's going to have a lot of session data. But the problem with this is they all have something in common, right? They all share the same source device ID, right? So we have a problem here because all that data is going to be sent to the same chunk, or even worse, adjacent chunks. So now we've created a hotspot, right? So that's one possible cause. The second possible cause is what we call a common manufacturing OUI. And OUI stands for Organizational Unique Identifier. And this manufacturing OUI is used to identify which manufacturer manufactures a certain device. So I've highlighted it in red on the right-hand side, the 005056. That is a manufacturing OUI. You punch that into Google, you can find out who manufactured this device. So let's say, for example, that this manufacturer manufactures scanners. So now this brings us back to the first issue, where they're manufacturing what we call jumbo devices that have a lot of session data. But now we have a lot of these deployed in one environment. And again, all of the session data is going to be represented by a similar device ID. They're all going to start with the same 6 characters. So again, we're going to have all the session data probably in the same chunk or adjacent chunks. And again, we have a hotspot. So let me show you what this looks like. So here's a very extreme case of one of our clusters that shows chunk distribution. So this shows how many updates per day per chunk that we have in our cluster. So it's pretty clear to see that this is not a horizontal line. We don't have even distribution. It's probably only a handful of chunks that take up the majority of the workload, right? So now that we have this, we've been able to identify which chunks are the problems. But how do we get this report in the first place? So with the help of the Mongo team, they've helped us set up this chunk info collector job, right? And this job runs daily and helps us generate reports like you just saw on the previous slide. So this job will scan every chunk in our cluster and collect meaningful information like size of the chunk, number of objects in the chunk, number of documents written in the last 24 hours. And this last point is very important to us because this tells us how active a chunk is, how many times it's been updated or written to in the last 24 hours. And we're able to take this data and visualize it to tell us which ones, which chunks are the most problematic for us. This one, for example, shows us the chunks with the most objects in it. We have a graph here that shows us the chunks that are the most active, right? Which ones have been written to the most in the past 24 hours. We're able to identify jumbo devices, right? Which devices give us the most session data. And again, this one also, you can probably notice in the device ID column that we also have another problem here. They all share the same OUI, or most of them share the same OUI, 005056, right? And now we can look at the shard column and notice that they're all in the same shard. So now we're really, we can really have proof that we're experiencing a hotspot, right? And for further proof, we have this chart that shows us the grouping of OUIs, right? All the devices for this OUI, how many do we have in each shard, right? So now we've identified that we probably have an issue with our sharding key, right? We're grouping together alike devices that are potentially harmful for us and causing imbalance in our shards. So currently right now, we're doing a lot of development, a lot of R&D to fix this sharding key. We're doing a complete redesign. But until that long-term fix is in place, what we can do is, since we have all of this monitoring to show us which chunks are the hot chunks, what we can do is manually help balance them out. We'll manually split these chunks and manually move them off the problem shards to help balance all the chunks out. And the last point I want to point out is we like to monitor largest documents. And this is very helpful for us because especially in our customer-facing collections that need to be very fast, we want to keep those collections short and clean, so they're very responsive. So this is just a way for us to keep an eye on huge documents that could potentially use up a lot of memory in Mongo. And let's return back to this image here that originally we showed for representing an unhealthy cluster, right? So after implementing all this monitoring, we were able to identify the problem, put in fixes, short-term or long-term. Now we can see that our write tickets are healthy again. We have available write tickets to process all the commands coming out without adding extra resources to Mongo, without adding sharding, and our workload is staying the same and even growing at this time. Now our queued writes, we don't have anything in the queue. We don't have any lag built up in the pipeline, which means we're happy and our customers are happy. So now let's recap. Why make the move to Atlas? It's a managed service, it's very scalable, and for us it was very cost effective. It comes with a lot of monitoring tools, and it comes with an expert knowledge base of around MongoDB. How have we improved with Atlas? We've added a lot of visibility into our cluster, which has helped us to identify problematic commands and improve efficiency. And as you've seen on the previous slide, now our cluster is very healthy and stable. So what's next for us in the IoT team? We are going to keep expanding monitoring and visibility because I feel like you can't have enough monitoring. Right? I just don't believe in that. We're going to continue working on sharding key enhancement. Our monitoring has shown us that we have a problem. We're experiencing hotspots because of common OUIs and because of our sharding key. So we're going to keep working towards this long-term fix. And these last three, materialized views, Mongo Search, Atlas Online Archive, these are all amazing features of Mongo that really excite us, and we feel like they can help us implement new features down the road that are in very high demand, from our customers. So yeah, that's the end of my presentation. I hope you learned something. I hope you found it interesting, and possibly you can take away some of the common practices that we've been accustomed to. So yeah, thanks for listening.
Raise your hand, I'll run the mic over. I still have to burn off that tiny cupcake from lunch, so put me to work. Questions? Yes.
Hey, I was curious to know if you try to use something like serial numbers instead of the OEM ID for, to try to get rid of the hot clusters.
Right. So I don't think that was an option. I think that's something that we can definitely look into. I don't know if it's maybe that not all devices may make their serial numbers available, but I think device ID is something that's very common in every device, and it's something that I think we're going to keep in the sharding key, but we're just going to try and randomize it as much as possible and not make it predictable as it is right now.
Any other questions? Great.
Just curious, have you open sourced any of your tools, your monitoring tools, and those kind of things?
We haven't. No, these have all been developed within the past couple months, and mostly the backbone of this has been from the Mongo team. So we kind of just built on that. But no, it's all been in our private repositories.
Any other questions? Excellent. Well, I'm sure you can find Aaron for a little bit afterwards. Thank you so much.
Thanks, Chuck.